Hi. Hey. I'm not between you and beer, am I? There's like one more after this. I'm between you and beer. I'm so sorry. I have a lot to tell you, so I'm going to get started as you guys are coming in. My name is Hooman. I'm the VP of Technology at Fastly. The title of this talk was quite accurate when we first came up with the abstract, but since then, a lot of the information that I'm going to give you today has been surfacing from here and there, so I actually had to change the name of the talk slightly to make sure that I cover my ass. Despite this, if you're anything like me, probably most of what you've heard about HTTP resembles this. A lot of promise, a lot of potential, a lot of great things about how it's going to solve all our problems. As a matter of fact, for me, it felt like clickbait after a while. The idea behind this talk was to sort of take a step back and take a slightly more objective view of the protocol, take some practical considerations into scope. I have a bunch of data I want to share with you that we're going to sort of go through together. And the idea is ultimately to have a better understanding of the good and the bad. My assumption is that you're generally familiar with web performance topics and familiar enough with HTTP2 to have been curious enough to come into this. So I'm not going to cover a lot of like super basic stuff, but I am going to cover HTTP2 and some core concepts before I get into some details about its features. HTTP2 was ratified as RFC 7540, I think right around a year ago. If you don't already know, it's a binary protocol. A binary protocol means that everything is binary, obviously, but everything is in a well-defined, predeterministic place. So as you're developing, things are really, really easy to find. This is a good thing because you don't have issues like text parsing and dealing with like line termination and things that you had to do with HTTP1 before. The bad thing is, gone are the days of telnetting to port 80 and typing something in and getting something back. So troubleshooting got a lot more difficult, not because of this, but also because of the security side, which we'll talk about in a second. So you need tools now to do any sort of debugging. Things got a little bit more difficult on that side. HTTP2 runs over a single connection. It kind of looks like this. The client starts a connection, a TCP connection to the server. Everything for an HTTP2 connection and all HTTP2 communication between a client and a server will happen over one single long-lasting TCP connection. The idea here is that this will give you better congestion management because you don't have multiple TCP connections vying for the same network resources. Everything will also happen over TLS. This is not mandated by the protocol, but all the browsers basically said we're only supporting the TLS version of the protocol. So using ALPN, which is a TLS extension, there's a protocol negotiation during the SSL handshake, the TLS handshake, and then the two sides start speaking H2. And you can reuse a connection. So to maximize the number of requests that you shove over a single connection, you can actually reuse connections. And the rule is that if two different host names resolve to the same IP address and have the same certificate, you can share and coalesce those requests over a single connection. Over that connection are these things called streams. And you can have many streams simultaneously sort of going back and forth between peers over a single connection. Streams are essentially virtual channels for communication that roughly translate to a single request-response transaction, a request-response exchange. Either side can initiate a stream, and every stream has a stream ID. If it's an odd number stream ID, it was a client-initiated stream. If it was an even number stream ID, it was a server-initiated stream. And stream 0 is reserved for the connection itself for management reasons. The only rules are they have to increment and you can't reuse. With the bit space, that's about 1 billion streams per peer. So hopefully you'll be able to do that for the lifetime of the connection. The smallest unit of communication in H2 is this thing called a frame. Every exchange happens over frames, and frames sort of flow back and forth between peers, and they all carry a stream ID. And that associates them with the stream that the communication is supposed to be over. The best way to explain frames is kind of like this. Imagine that this was your H1 communication between a client and a server. You sent a bunch of request headers. The server sent you a bunch of response headers with a bunch of response body. In H2, you send a headers frame with all your request headers, and in response, the server sends a headers frame with all the response headers and a bunch of data frames with all the actual data, the payload. There's a whole bunch of different frames defined by the protocol. I'm not going to talk about all of these. I've kind of talked about data and headers frames, I kind of want to point out the settings frame. It's this like management frame that the two sides exchange to sort of communicate different capabilities with each other. It's things like how many concurrent streams you can have a peer is expecting to see on a single connection, what your maximum frame size can be, how big your HPAC table is, whether you support features like push. That's what the settings frame is for. So what does the protocol flow look like? Well, with H1, we had a single connection, and we would send a request, and the server would send a response. That's how H1 worked. With H2, we have a single connection. Instead of sending a request, we send a headers frame with all our request headers. It's got a stream ID, and the server responds with a headers frame with the response headers and a bunch of data frames. That's the payload. Everything has a stream ID, and that's how the two sides know what the communication is. Now, with H1, we had this one connection, and nothing else could happen over that connection for the lifetime of that request-response exchange, right? This was the big problem. Because that connection was blocked while this outstanding request was being processed, we experienced a phenomenon called header line blocking. So nothing else could happen over that HTTP1 connection. So we had no concurrency, we had no multiplexing, we had no interleaving of responses. So to get concurrency, what we did is we opened a bunch of connections at once. Browsers open up to 6 connections between a client and every single host. And we even sharded to get more than that. So we can have a lot of concurrency happening at the same time. Because our web pages have a lot of assets, we have a lot of fetching to do. So in H2, we don't need to do that anymore. What happens is frames flow freely between peers. You can have data frames, you can have header frames, you can send multiple header frames in a row, and essentially pipelining for requests. Data frames can come back interleaved. You can have data frames from one stream come after data frames from another stream, and you can interleave them essentially. Somebody thought this would be best represented as candy. So this is a delicious analogy that sort of explains this concept. If you ever looked at waterfalls, which is, I hope, true for all of you, this is an HTTP1 waterfall that looks like this when you go to H2. See, there's a lot of things happening at the same time. So concurrency is what H2 is giving us, and all those things are happening at the same time. If you're like me and love looking at wireshark captures, this is what it looks like in wireshark. Notice that frame all the way at the bottom where there's a whole bunch of header frame, TCP packet at the bottom. It's got a whole bunch of header frames. Those header frames are essentially pipelined response headers, all coming at once from the server before the server sends me any of the payload for those particular streams. Pretty much every browser now supports H2. It's on by default anymore, and all the servers are kind of supporting them too. Apache and Nginx both have modules. If you've never heard of this server called H2O, I highly, highly recommend you check it out. We use it at Fastly. It's a fantastic server. It supports both H1 and H2, supports all the H2 features. It's a great, great server. There's a whole list of all the other servers on Wikipedia. And if you're using a CDN, which again is, I hope is true for every single one of you here, because CDNs are good, talk to your CDN, because they're the ones that need to be doing that H2 termination for you. Okay, that was a crash course in H2. Probably the most important or talked about feature of H2 is performance. H2 is supposed to make everything faster for us, and initially we sort of believed that it was going to turn everything faster sort of by default. All you got to do is turn it on, don't need to change anything, everything's going to be faster. I'm plagued with the disease of cynicism, so I had to see this for myself. So what I did is I started with what should be the perfect page for HTTP2, and that's a page that basically has very little rendering on the browser side. No scripts, no CSS, just 110K images coming down the pipe. That's it. Very, very simple page. This is what the waterfall looked like before, and that's what the waterfall looks like after. And if you ever decide to do this as an experiment for yourself, I highly recommend that you use a different image than the one that I picked, because these look amazingly cute when you start the process, but I can't tell you the horrors of the nightmares these induce about 10, 20, 30 times after you've done this analysis. So please pick a different image. Just pick a transparent one. Look at a white screen. So to do this test, I used web page test. How many people are familiar with web page test? Thank you. Great. If you're not, please familiarize yourself with it. It's basically a synthetic testing tool that emulates real-world conditions. I use sort of the default profile for web page test, which is 5 megs of download bandwidth, 1 meg of upload bandwidth. And I use 40 milliseconds of latency because roughly in the US, 40 milliseconds is the median across a whole bunch of CDNs. I used Chrome, and the idea was to test H1 versus H2. Now, if you've used web page test before, you can do like 3 runs, 5 runs, 10 runs. If you have a private version, you can do like 20 and 30 runs to sort of see patterns in the data. You'll see variance because tests give you variance. I didn't want to do 3, 5, 10, or 11 runs. I wanted to do 270. So I did 270 runs each of H1 versus H2, and this is a scatter plot of document complete time for this page. Can you see this? Is it clear? Clear enough to see blue versus orange? Okay, so blue is H2, orange is H1, and okay. Seems like it's a little bit fast. I kind of was hoping for a bigger separation because of all the talk, but okay. I think it's fair to say that in this graph, H2 is slightly faster than H1. The pattern shows this. And this is document complete time, so metrics matter, and we'll talk about that in a second. Now, you've probably seen something to this effect with the same conclusions of like H2 seems to be faster, sometimes a lot faster, sometimes not so much, from various sources. What I had never seen before is what would happen to this not only with inflicted bandwidth and latency, but also with packet loss. Packet loss is a thing that happens in the world, and what's the effect of that on this? So let's go back to our web page. This is web page test if you haven't seen it before. Web page test gives you the ability to inject packet loss. That's great. I was using web page test. So let's inject some packet loss. So I started injecting packet loss. This is our scatter plot to start with. Let's put that in the corner, and let's start adding packet loss to this. We don't change anything else except packet loss. So 270 runs, H1 versus H2 with packet loss. This is with 0.5% of packet loss, 1% packet loss, and 2% packet loss. The story changes, right? And that's really interesting. Okay, what if this is a Chrome thing? Let's try Firefox. Pretty much the same thing, right? Okay, great. A lot of people are saying that H2 is supposed to help mobile connections and slow connections and higher percentiles. Let's do that. Here is a slow 3G connection with poor performance, low bandwidth, high latency. Let's see how this guy reacts. Pretty much the same. So again, H1 does better when there's packet loss involved. You see that little bump on the left side? What is this thing? Get this out of the way. See that bump on the left side where H2 sort of behaved the same as H1? Unbeknownst to me, somebody turned off our H2 capabilities during this test. So those are actually H1 sample points that look like H2 because of the way I was testing. I thought about taking it out of this, but I actually kind of like it that they're in here. They show the pattern sort of well. I'm going to switch gears. Instead of showing you scatter plots, I'm going to show you CDF graphs. In case you're not familiar with CDF graphs, it essentially graphs on the y-axis percentile versus the value on the x-axis. So what this means is the 50th percentile of the blue line on the upper left graph is roughly around 2,000 milliseconds. The 50th percentile of the orange graph is roughly around 2250 milliseconds. And this graphs all the percentiles for each of those runs. Blue is H2, orange is H1. Get used to these colors. I'm going to show you a lot of these. And look at the pattern as packet loss is added. And as you sort of visualize it, as you look at this, if you're to the left, you're doing better than if you're right. The ideal scenario is a straight line up and down, which means there's zero variance, but there's always going to be some level of variance. This is Firefox. Let's add Chrome into the picture. There is a separation between Chrome and Firefox. I'm not going to get into that. I just want to sort of point it out, and you'll see this as I show you more of these. Get used to these colors, because I'm going to flash a whole bunch of these in front of you. Blue and red are H2, orange and green are H1 for Firefox and Chrome. So again, blue and red versus orange and green. To make things a little bit easier to digest, I made a scorecard with the extremes. So 0% packet loss versus 1% packet loss, 2% packet loss. Obviously, we see that with document complete time, H2 is not doing so good with high packet loss. Now, I'm a good web performance citizen, and I know that doc complete isn't the only metric I should be looking at. I saw a great talk from Tammy Everts and Pat Meenan that said DOM content loaded seems to be a very good indicator of e-commerce conversion. So I want to make sure I look at that. And I also like speed index. If you've ever used web page test, speed index is a great metric. It's an aggregate metric that it calculates for you based on visual completeness of the page. So I added those two in the mix, and here's how they sort of fare with 0% versus 2%. Now, I'm not stoked about the H1 winning with the 0% packet loss. That's a little disheartening to start with. But clearly we see that packet loss has an effect on the performance of H2 on the right-hand side of this chart. Now, certainly with certain metrics, H2 holds up, and one of the lessons that we're going to learn here is that a lot of this depends on the metric that you choose. Well, why is this happening? Well, it's happening because this is actually an incorrect and misleading analogy. The actual analogy should look more like this, right? What we're doing is we're replacing 6 concurrent connections with a single concurrent connection. Sure, we can do a lot of things over that one connection, but we had 6 concurrent channels before. Look what happens to a single TCP connection over the lifetime of its connectionness. This is graphing on the y-axis the congestion window versus time. The congestion window is there's 4-year courses on this, but I'm going to give it to you in 10 seconds. It's essentially the amount of data a server can send safely without any loss on the network, or what it thinks is the right amount of data to send. What normally happens over the lifetime of a TCP connection is the server ramps up until there is natural loss, then it slows down with the ultimate goal of sending enough packets onto the network without incurring loss. That's what it's trying to do. So you can see this convergence, and this particular server is ramping up and it figures out the right C window over this connection. This is with 0% packet loss. I inject 1% packet loss into that same connection, and that's what the graph looks like. So imagine that an H2 connection is subjected to this sort of behavior. It doesn't matter if you're interleaving. If the server says, I can't send a packet onto the network, all the frames that are sitting there are stuck behind that decision. So what's essentially happened is we've moved head-align blocking from HTTP to TCP. This is not a new concept. The authors of the protocol knew that this was a byproduct of the design and decided that the net was going to be positive. And sometimes it is, but what I'm pointing out here, I think, is situations where it's not. Imagine if you have 6 concurrent connections running at the same time and they're subjected to the same 1% packet loss. They're all incurring and suffering from it in their own pace and their own context. And if you sum up at any point in this graph the total C-wind of those connections across all 6, the sum is always going to be bigger than any one of those. What's happening is as multiple connections are incurring packet loss, some are suffering and some are suffering differently or at a different time. And that's why I think we're seeing in certain situations, certainly with packet loss, H1 fare better. Now, okay, my test was simulated, so that's not good, but that's what we have, or that's what I had. And it was a totally fake page, so I wanted to do real pages. So I took 8 real pages, so 8 sort of home pages from 8 real sites, and I tested them with 16 different bandwidth and latency combinations, so all sorts of different broadband and all sorts of different not broadband, like mobile-type connections. Each of them incurring those 4 different packet loss profiles. I tested Firefox and Chrome. I only tested the TLS version of HTTP1. Remember this, everything I'm going to show you is the SSL version, the TLS version of the HTTP1 site. There's an inherent performance loss, tiny bit, when you go from HTTP to HTTPS. And we're not even considering that. We're just going to consider the SSL, the TLS version of the site to H2. And I collected a shitload of metrics because that seemed like the right thing to do. And I ran each of those for 300 to 400 times. That adds up to around 1.2 million web page test runs in a big database. This is a fork. It looks a lot like the one I wanted to shove into my eye sockets as I started looking through 1.2 million data points. It was very difficult because I was really, really hoping that patterns would emerge and I could come here and give you these amazing lessons to take home. I can't do that, spoiler alert. But I did decide that what I'm going to do is I need to sort of limit the data set to something that's analyzable. So I divided the pages into 3 different types. There's a few of the sites, a few of the pages where 75% or more of the requests of the assets were moving from H1 to H2. There was the second bucket that was about half the request, and there was a third bucket which was slightly 25% or less. I only looked at 2 profiles. Not totally arbitrarily, I sort of solicited some advice. So it's a general broadband profile with 5 meg down and 1 meg up, and a general 3G profile, a slow 3G profile with 780 down and 330 up with high latency. And I looked at those 3 metrics that we talked about earlier. So I'm going to go through these 3 sites with you and sort of show you those CDF charts for each of them. That's a lot of slides with CDF charts. I'm kind of going to race through them, but I have scorecards that'll outline it all for you and show you all the beautiful results. First was a page on the Fastly website. It was a page that we show off all our customers. That page has about 130, 135 resources. It's about 3 megs. And about 75% of those were on the root domain, and that's what I was moving to H2. It roughly accounted for 2.5 megs of all that data. This is what the waterfall looks like before and after. I have 6 CDF charts I'm going to show you. I'm going to show them to you quickly. Here is the .complete one. Just train your eyes on sort of and I'm sorry if you can't see the blue thing, but I think maybe you can see it. Train your eyes on blue and red versus orange and green. So that's H2 on Firefox and Chrome versus H1 on Firefox and Chrome. So blue is H2, red is H2, orange is H1, green is H1. So this is .complete time with broadband, DOM content loaded with broadband, speed index with broadband, .complete with 3G. This is DOM content loaded with 3G. Actually, in this case, if you look at the bottom right, H2 sort of holds up okay in this case. And speed index with 3G. Okay, that's too many lines. Let's sum it up. Here's the scorecard. It kind of looks similar to what we had with that fake site. Again, not cool that H1 is coming on top with 0% packet loss. That probably blows away some of our expectations. But certainly we can see that packet loss has an effect. I can't tell you who site 2 is because I tested it without them knowing, and it'd be unfair for me to tell you who they are. I can tell you it's a travel site. About 100 requests to the onload timer, 1.7 megs or so, and about half of those were on the root domain or one of the subordinate domains that I could move over to H2. They accounted, however, for about 75% of the payload. This is what the waterfall looks like before and after. You can see sort of that top area where the concurrency occurs and requests move over to H2. Again, let's go through these. .complete tie with broadband. Again, blue and red are H2, orange and green are H1. .complete with broadband, DOM content loaded with broadband, speed index with broadband. It's a little weird that all the lines are really, really close to each other. You kind of was hoping for more separation, but this is what happens. Here's 3G. This is .complete, DOM content loaded, and finally, speed index. And again, in this case, you can see H2, that red line, which is Chrome with H2, sort of holds up across all 4 profiles. So this is a case where H2 sort of holds up fine. Probably an artifact of the way the resources are ordered or being rendered by the browser. This is what it looks like on our scorecard. H2 fares relatively well with 0% packet loss, but again, I don't like those reds there. And certainly a lot of red with 2%. I think the point is kind of becoming clearer, but I'm going to keep driving it, so I'm going to do a third site. And with the third site, this is a media site. A lot of requests and a lot of third-party content. So only about 25% of those requests are moving over from H1 to H2. This is what the waterfall looks like. It's huge. And there's so much shit going on here that you can't even tell which ones have moved over. But trust me when I tell you about 25% of the requests moved over to H2. Let's look at our really, really friendly CDF charts. Here's .complete with broadband. And in this case, you can kind of see again with the Chrome and Firefox, H2 sort of hold up okay with 2% packet loss. That's kind of cool, except we moved a lot less resources over. .complete time, this is DOM content loaded with broadband, speed index with broadband. Let's go to 3G, .complete. This is the noodle graph with DOM content loaded, speed index, and our scorecard. In fact, let's put all of them on a scorecard. So here's all 8 sites. The first of each of the buckets, so site 1A, 2A, and 3A are the ones I just went through. I didn't go through the CDF charts for the other ones because God have mercy on all of us, but that's sort of the way everything's scored out. So here, let's look at just broadband. Let's look at just 3G. and here's everything together. So I'm just going to leave this on for a second so we can sort of absorb it in. Not stoked on all the red things on the left side with the 0% packet loss. So I was kind of hoping to have sort of all greens there. Certainly there's an effect on performance when we inject packet loss into the network, and 2% is, in this case, the extreme that I chose. I didn't go any further than that. And definitely a lot of inconsistencies. H2 holds up in some cases and doesn't hold up in others. What does it all mean? I don't know. It just seems like packet loss is a thing. And certainly it seems like metrics that are later in the page are being affected more than metrics that are early in the page. But I want to be careful with that declaration, because in the lifetime of a TCP connection, a page is a really short time. What would be interesting is what this looks like 7, 8, 10 pages into a flow, like into a site as you navigate a site. And I don't have that data, unfortunately. I hope to have it at some point. We've seen lots of exceptions, right? We saw places where H2 held up with packet loss. We saw places where H1 was winning with no packet loss. And we definitely saw that Firefox and Chrome didn't behave the same. That's an interesting issue. I have a theory of many that if I have time, I'll share with you guys a little bit later. And it's probably safe to say that when you look at data like that, there's more questions than answers, unfortunately. I really wanted to stand up here and give you these magnificent, great rules of thumb, but I can't. There's no thumbs to be ruled. Now, the natural next question that you probably are asking is, great, packet loss seems to be a problem. What's it look like in the real world? Well, packet loss is actually difficult to measure, but we try to at Fastly, and we sample a whole bunch of requests that flow through our network. Let me narrate through this graph for you. This is a bunch of sampled requests. We keep track of it on a request level. In the United States, so this is about 8 million requests. All these requests were 100 packets or more. So, relative like that, what is that, 14K or more, roughly. What you're seeing is up to 60 milliseconds of round trip time between the client and our servers. That's about 70 percentile of the US. So in our network, about 70 percentile of the US is experiencing 60 milliseconds or less. What you're seeing here is the orange band is the percentage of requests that experience 0% packet loss. The blue band is the percentage of those requests that experience 0 to 1.5% packet loss. And the orange band is the percent of requests that experienced more than 1.5% packet loss. So roughly 20% of these requests, and this is a sample of 100 packets or more, requests with 100 packets or more, about 8 million requests, that experienced, 20% or so experienced some level of packet loss. That is an interesting fact. It could be a lot worse. It's good that it's only 20%, but it is happening sort of out in the wild. It's a difficult thing to measure. But this is sort of a good proxy for it, we find. I'm not the first person to talk about packet loss and its effect on H2, or the fact that H2 doesn't necessarily perform best. I have a whole bunch of reading and homework for you guys. Here's a bunch of papers that sort of talk about things like this. Everything from how packet loss affects H2 to cases where H2 didn't perform better. Now what? First, a word of caution. I'm not going to stand up here, like I've been saying, and draw these magnificent giant conclusions, other than the fact that packet loss seems to affect performance, and H2 isn't always as fast as we had sort of hoped it would be. I think that's as far as I'm willing to go. And I was really tempted to go further and really dig into those 1.2 million rows and find out more patterns, but I stopped for a reason. This was all simulated, right? Everything that I did was simulated. There were real pages, but it was simulated conditions with simulated, like Chrome, but on a simulated sort of connection. Packet loss in the real world is slightly different. Packet loss happens when buffers bloat in routers and overflow. Packet loss happens because you turn on your microwave at home and your Wi-Fi router decides to drop a packet. And what I was injecting was uniform packet loss. So packet loss is different in the world. Conditions are different in the world. This was all simulated. And users aren't all broadband users or all 3G users. Your users are a mixture of all these things. So there is a lot of variance in your worlds. And none of this, nothing beats real world data. We need real world data to draw some of those conclusions, which means your mileage will definitely vary. So the biggest lesson out of all of this is don't listen to anything anybody says. Anybody. Don't listen to anyone, including me. Do this for yourself. If I was going to leave you with one thing, is if you're interested in this, you have to do it for yourself to understand the benefits. I'm going to preach more about this later, but I think this is the biggest lesson here. Patrick Hooman from the Financial Times did it, and he released this. This is a graph of his doc complete time from real users, document complete from RUM, and this is the effect of H2 versus H1. And he found that when the RTT between a user and a server's was higher, H2 was helping more. There's two interesting things here. One, it's unclear what percentage of his users fall into each of these bands, so it's difficult to tell. And second is, it seems like H2 is not creating a lot of performance value on the left side of 100 milliseconds. And all CDNs in the world try to live on the left side of the 100 milliseconds, and everybody wants CDNs to do H2. So this is kind of a funny thing to me, but it's out there. It is what it is, and we're doing H2. All the CDNs are going to do H2. We're all going to end up doing H2. This answers the first question, though. It's probably fair to say that the higher percentiles of Patrick's users were falling into the higher RTT times, and those are the users that were getting benefit. And I implore you to do this stuff for yourselves and figure this out. This sort of lines up with what I'm hearing from the pundits, if you will, that we should expect more performance benefit at the 95th and higher percentiles, and we shouldn't expect a lot at the median. But again, some of the stuff that I did doesn't necessarily match that either. So again, it's going to vary because there's so many variables here. It really depends on your users. I had 2 conversations within 10 minutes 2 nights ago at an event of 2 different people with big sites, an e-commerce site and a media site, that did this stuff themselves and found H2 to have 0 to no benefit for them. Marginal was the word that was used. That doesn't mean they're not going to use it, because there may be other benefits they find, but we just need some caution when it comes to performance. To encourage you to do this on your own, instead of sitting here and going through 1.2 million data points with you, I made you a gift. So here's a tool, and let me just preface this with this. I don't know how to code, like at all. So I wrote this really, really hacky Python code that I gave to Mark Tidoro, who I work with. I'm lucky enough to work with, who's patient enough to clean it up for me and make it respectable. This is a very simple tool. You basically put in your connection profile, you put in your site, it uses web page test, whether it's your private web page test instance or the public one, does a test and spits out a PDF with scatter plots of all the core metrics. Now, this is again simulated. It's a little, it's a glimpse into what reality may look like, but I really, really implore you to do this for yourself, for your users. And if nothing else, you don't have to compare H1 versus H2, just figure out what the benefits are for you. This is probably a good time to talk about Quick. I'm not going to dig too much into Quick, but Quick is the new protocol that Google is sort of spearheading. It's now in the standard track. Quick is essentially a new transport for HTTP over UDP. And the biggest motivation for Quick was that congestion control, which is the thing that controls how TCP sort of responds to loss events on the network, was moved in Quick from the kernel, which is very difficult to iterate at, to the user space. So one of the things that Quick does is it lets you be very agile and very iteratively for your algorithms. So this has allowed Google to do a lot of iterations. It's now in the standard track. There's a working group and everything. It's going to change things up a little bit because it, for the first time, sort of blends application layer and transport into one thing. So it's good and bad. It's probably going to be better for performance, but it's going to make things a lot more complicated. OK, let's talk about server push. We're going to move on. Performance. Put her to sleep. Let's move on to server push. Probably the second feature that gets talked about the most. We have always been very, very optimistic about server push and the promise of pushing things to the browser. The basic notion is that the server has the ability to push data to a browser before the browser requests it or even knows it needs it. So the idea is to get things into the browser cache. Only servers can push, and it's a hop-by-hop property, meaning if you have a middle box, the way that middle box pushes to a client can be different than the way that middle box gets pushed to from a server. The ability to do it is negotiated in a settings frame. Remember I talked about settings frames earlier? Here's what it looks like. It's on by default, so the only time you actually advertise it is when you don't support it. So this is an example of a client that doesn't support push. Push happens with the use of a special frame called a push promise, and this is what the flow looks like. You as a client send a request, it's a headers frame that comes in for, let's say, the index HTML. Before sending you the index HTML, the server sends you a push promise frame, which is that big orange thing up there. The push promise frame is associated with the stream that you made the request on. It has a promise stream ID, which is going to be an even ID because it's a server-initiated stream. And it has the request headers you would request if you were going to make that request on your own. So it's the would-be request headers that the browser would send if it was to naturally make that request. The only rule is the push promise has to show up before the thing that references what's being pushed. So if I'm pushing CSS, CSS1.css, I have to send the push promise frame before the HTML or the headers that reference that CSS. I don't need to send the CSS, I just need to send the push promise to sort of let the browser know that this is coming. That's the idea. In this case, we send the push promise, then we send the headers frame with data from stream ID 1, the HTML, and then the headers and data from stream ID 2, which is the push stream. And again, because it's H2, we can interleave those with the data from stream 1. This is kind of what it looks like in DevTools. Those 4 first requests that you see, those are pushed responses, pushed assets from the browser, from the server to the browser. You can see that the initiator over there says that it's push, and Chrome DevTools actually shows us this little thing too that says it was a push and how long it took to receive that push. So that's how push works. There's 2 big questions with push, outstanding. The first is, what the hell do we push? And that is actually outside the scope of the protocol. The protocol intended to just create a mechanism for you to push. It's kind of up to you to figure out what to push. That doesn't mean it's not a question. It's actually a big one. And second, it may be a bummer, but it turns out that push and browser caches don't work well together. In fact, the push cache and the browser cache are 2 different places, and they don't know about each other. So what happens is the protocol allowed a mechanism that lets you say, I'm about to push you something, and it has a mechanism through the use of a reset string frame for you as the client to tell me you don't want it because you already have it. But I have yet to be able to generate a reset string frame from a browser. The browsers just don't know that they have it in the cache. And even if they did, it would be too late, right? If I'm pushing you something and you're going to tell me you don't want it, and I've started pushing that stuff down to you, it takes a whole RTT for me to get that, fuck off message from you. So it's too late already. I've shoved a bunch of shit down the pipe. So let's see what this looks like. Here is a no push scenario. First view, cold cache. Here's a page with 10 images and 4 CSS files. And this is what it looks like. H2 connection. I load everything into the browser. And now I'm a very good performance citizen. I put good caching headers on this. And this is what the repeat view looks like. Okay, just the HTML, which I chose not to cache in this case. If I push, here's what the waterfall looks like if I push. Those first 4 assets are being pushed. Great. I got some performance benefit from pushing them. But the repeat view kind of looks like that, which means I push them again. So this is redundant data going over the wire. So this is a problem. The fact that the browser cache isn't able to somehow communicate to me what I should be able to push is a problem. Now, let's pretend that we have that situation. Let's pretend that we figured out what to push. It's a problem. I don't claim to have an answer for it, but let's pretend we figured this out. What are the actual practical use cases for push? Well, I could think of 3. First and foremost is essentially push becomes a replacement for inlining. Inlining was a problem because when we inline assets into our HTML, we lost the ability to cache those independently, right? We had to send it down with HTML. Well, if I push those instead, I have the exact same performance profile, but I can take those resources and now have it in the browser cache. That's a plus. That's a thing that helps me because I don't need to keep inlining those resources. And I don't need to pay the penalty for fetching them. That's the first use case. The second use case, somewhat similar, is to push resources essential for this navigation, for this page, the page that I'm on. Very similar, if you're familiar, to the link rel preload mechanism, which essentially initiates the browser preload to go fetch things before it's parsed the entire HTML. In fact, Most servers use link rel preload headers as a signal for what to push. So if you have those headers in, you will probably signal your server to do a push. There's a lot of discussion in the community now to actually add a second context here, a second directive, like a rel push, to sort of separate the preload scenario from the push scenario. But today, most servers just use that as the hint. Ours does, and I think Nginx does as well. This essentially saves you one round trip. And here's what the waterfalls look like before and after. Why is it one round trip? Because it's H2, because we can send things concurrently. So when the browser sees that it needs them, it's going to send all the requests for those things that we would have pushed otherwise at the same time, and that takes one round trip to get to the server. So by pushing things, we save one round trip. It's a performance saving. We like to save round trips, but it's not as magnificent as maybe we would have thought. What's more interesting and probably cooler is the idea of pushing things to the browser during server think time. What's server think time? Server think time is the time it takes for our server to assemble an HTML for us. Or if you're using CDNs, the difference from the edge to your origin. You go through an edge server, you got to go all the way to origin. This is not necessarily close to your users. And during that time, you can do some pushy things to the browser. I made an exaggerated waterfall for you to sort of see this in this concept at play. This particular HTML takes 3+ seconds to render on the server, and during that time, I would have had this massive white space that I didn't do anything with before. Now I can use that space to push things down to the browser. This is a kind of a good use case because I can take the time that it's taking for the server to render to push things. Now, if you talk to me about HTML time, I will do everything I can in my power to encourage you to cache your HTML at the edge in your CDN, because that's ultimately better for you and better for your users. But there are scenarios where you can't physically do that because of reasons that may be outside of your control. In those cases, push is a good mechanism to get things to the browser before the server sends references to them. So this, Yoav Weiss has a very good blog post about this, by the way, that talks about this more. I would highly suggest you guys go read that. It is not a trivial thing to do because it's essentially an asynchronous operation. Two different things have to be happening at the same time. A push needs to go to the client while a request is going to the server. Separating that stream isn't trivial with web servers. So if you're interested in this, talk to your CDN because it's not a given that they support this. There was also this notion early on that we can use push for next navigation, for what we're going to see in the next page. Although push can be used for that, we already kind of have these good mechanisms called resource hints in place, things like rel prefetch and rel pre-render that allow us to use idle time on the network to fetch or pre-render things that we think the user is going to go to. So even though we can use push for that, there's already mechanisms in place. And even when all that's figured out, we still have our two big questions. What do we push? We still don't know. Google published a paper. It's actually a really nice paper. It's not totally all the answers, but they did some studies, and they have some rules of thumb, general rules of thumb. It's a better place to start than zero. So I highly recommend you guys read that. I'll make sure these slides are available afterwards because there's a lot of references in here. And to answer the question of what do we do in case the thing is in the browser cache already, we know that the mechanism of the reset stream isn't really going to solve our problem. So there's two things I know about that are going to try to address this. One, H2O, the server I talked about, has this mechanism called Casper, which essentially uses a very smart cookie as a signal from the browser to the server about what the browser may have in its cache. It's a Bloom filter. It calculates a bunch of stuff in there. And that mechanism is actually the starting point for a new standard movement or a standard initiative called cache digests, which is essentially the same idea, a way for the browser to tell the server what it's got in its cache so the server can figure out what to push intelligently and not keep pushing things to the browser that it already has. I think one of the most interesting cases with push is the one we haven't thought about because the mechanism's in place, but it's possible that we can use it for creative things that are not necessarily page rendering things. And Facebook just released a video a couple days ago where they kind of did this and figured out interesting, creative ways to use push. So there's a link to it. You may have already seen it. I would recommend that you look at it and sort of figure out what they do. It won't probably match what you need from push, but it may give you ideas. Obviously, you see we're early in the life cycle of this protocol, so we have a lot of learning to do. And the more we look at these things, the more we publish these things, the more we tell the world, the better it is for us. Okay, let's keep moving. Is this helpful? Am I bumming you out? Is this okay, or is this like a serious bummer? Okay, we're all right. Let's keep going. Let's talk about HPAC. HPAC is the RFC 7541. and addresses the big headers problem, right? We had big headers, repetitive, bloaty headers. Let's solve the problem. There's two primary mechanisms in HPAC. One is that all headers are Huffman encoded when they're sent from clients to servers and backwards, and the other way in headers frames. And there are two tables that the two endpoints build. And the idea is that instead of sending like user agent is blah, 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 you send index 3. And that's all you need to send, and this is the way you get compression. There are two tables. There is a static table. It is very well defined. The definition will never change, and unless, I guess, they iterate the RFC. And it basically is the table that both sides start with. And then there's a dynamic table that you build as you communicate. And every new header value combination sort of becomes a new index into this dynamic table. It's a FIFO table, so things will get evicted from it if the size is overrun. That's the dynamic table. This is what the static table looks like. So you can see that there's 61 entries in it. Some are header name and value combinations, and some are just header names. And you can use this as a starting point to build new entries in the dynamic table. Now, one of the things that this mechanism promised early on was because you have the word compression in what it's doing, we assume that there's going to be performance benefits from it. There kind of is, but I kind of wanted to visualize it because it didn't click for me until I saw it. So let's look at bandwidth usage from the client to the server when you're using HPAC. You see that there is significant bandwidth savings when you use HPAC. This makes sense because most of the communication between a client and a server is requests that are headers. So we started indexing those. We started making requests that are this big into 1 byte. Obviously, we're going to see a benefit. Look what it looks like the other way. This is what it looks like from the browser to the server. This also makes sense because most of the data that we're getting from a server is payload, right? Not headers. So that kind of also makes sense. This is not a revolutionary set of graphs. But for me, it sort of made a lot more sense when I saw it. So I should be maybe expecting some bandwidth savings on the way to the server, but I'm not really expecting that many performance benefits on the way back. Dropbox published a blog post essentially to this effect. They said they turned it on for an internal application, and they had significant savings for their ingress bandwidth. And you can see there's not much going on the egress side. Some things to know about HPAC. That dynamic table defaults to 4K. And turns out that no browser changes it. So it stays at 4K. Look at this. This is Twitter's content security policy header. How big is it? That big. So half of the dynamic table gets taken up by one header when Twitter speaks H2. That means this thing is going to come out of that table because it's FIFO, and it's going to keep going back into the table, and over time, the benefits are probably going to be slightly less. There is a proposal called a site-wide header proposal that's going to address this, and the idea there is don't keep sending even the same index as you keep going through communication with the server. The things that are going to maintain throughout the lifetime of the connection, like user agent, just send them once, ever. So these are like site-wide headers, particularly aimed at server to client headers, because those are the places where bloat happens. Compression context is per connection. Remember this? This means that if you close the connection and open a new one, even if it's H2, you lose the entire dynamic table. This makes, if HPAC is beneficial to you, this makes keep alive timers that much more important. So they're a bigger deal now because you're going to lose HPAC context. And it's an attack vector. And there's a paper released from Imperva that really attacks the crap out of it and breaks it in all sorts of different ways. So it is a new attack vector. One of the complications that comes with H2 is stuff like this. And you can't turn it off. That's probably not a bad thing because without it, you couldn't actually pipeline requests because your requests would essentially overflow the client's CWIN towards the server. So the only way you can send 10, 20, 30, 40 requests at once is if you index them, essentially. Okay, one more thing. Probably the not most important, one of the most important and definitely least understood mechanisms in H2 is prioritization, which is a new mechanism that we didn't have before. The idea is that with all this concurrency, all this stuff happening at the same time, there's going to be contention. So we have to have a framework by which a server can pick and choose what's more important than what else. What's more important and what's not. So there's two mechanisms in priorities. There's a weight, which is essentially the priority of a stream, and there's a dependency. So you can build a tree, essentially, out of this. Stream weights and dependencies are communicated in two different mechanisms. One is through a headers frame. As you make a request, you can assign a priority and a dependency to it. Or you can change that with a priority frame, just on its own. A priority frame just dictates priority and dependency. And the spec goes out of its way to say it's only a suggestion. So it's basically a suggestion from the client to the server for ways to prioritize. The server is not obligated to observe those priorities, but it's a pretty good suggestion. I'm going to show it to you with a couple of examples. Here's one. Actually, it's not mine. It's from Ilya, so I'm going to give him credit. It's from his book. Here's a simple one. You have two streams, A and B. Those are their weights, and essentially everything is proportional. So in this case, stream A gets 3 times as many resources as stream B because it's 75% of the entire pool of resources. Here's example 2. This is dependency. In this case, the idea is that stream D gets everything, and then after stream D is done, you move to stream C. Here's one and two of them together. In this case, D gets everything. After D is done, C gets everything. And after C is done, 3/4 of the resources go to A, and 1/4 of the resources go to B. And let's keep going and make it more complicated. In this case, D gets everything. After D, E and C get equal resources. The fact that they're 8 in this case doesn't really matter. It's just the ratio to each other. And after C is done, which takes up half the resources that we have after D is done, that half, 75% of it goes to A and 25% of it goes to B. That's sort of how this works. It gets more interesting when you look at how browsers do it. Now, it's really difficult to look at browser trees, but somebody did it. So I'm just going to plagiarize and show it to you. Firefox does it really interestingly. Firefox starts with 1, 2, 3, 4, 5 streams that actually carry no request. They just sort of sit there as roots in a tree, and then they have subordinate streams that carry the actual requests. His name is Moto. He's from Yahoo Japan. He's a great contributor to the H2 community. So check out that presentation. It's great. This is basically stolen right out of it. And what happens is, as Firefox builds this tree, each of those sort of branches get used for different types of assets. So like JavaScript in the head, it's down a different branch. JavaScript in the body goes down a different branch. Images are a different place. HTML is a different place. I have no idea why they chose to do this, but it looks really smart. Like it looks like somebody put some thought into it. But I have no idea why it's like this. I just see it often. Chrome used to be like this. No dependency, but basically only priorities. Everything compared to each other dependent on the root node, which is how everything starts. It's changed since. In Chrome 53, here's what the tree looks like. And I know that's really, really hard to read, so I'm going to make it harder to read because that's the actual tree. It looks like that. That's for a page. So Frederick, who works at Fastly on our H2 team, put together a tool. It's a really cool tool that lets you essentially take Chrome internals, paste it into a file, and you get a picture out of it. So if you're curious and want to play, go play. That's how this was generated. What's weird about this tree is the extreme level of dependency created down the side here. Essentially what this means is that interleaving is dead down that side of the tree, right? Because what this means is that each node can't be operated on until the node before it's done. It means I can't do 2 things at once. I got to do one after another, which kills interleaving. So I'm not sure what the motivation behind this is. With Chrome, I just assume everything is just an iteration, that they're figuring things out. So I'm just going to give them the benefit of the doubt. But this is what it looks like. And it's not always like this. Sometimes it changes, and Canary looks slightly different. So I think they're in flux right now. And it may not come as a surprise that Microsoft has no dependency and no priority. Everything is just flat. This is over a year old, and I'm going to hope that what they've done since is slightly different. Priorities are really, really important because priorities are actually, they're probably one of the reasons that Firefox and Chrome were so different in those CDF graphs, because they just do priorities differently, and the servers are going to observe them differently. Okay. Let me just finish up by giving you some tools and resources, things to study up on if you're curious in this, which I'm assuming you are. If you haven't read this book, read it. It's magnificent to start with, but Ilya added an H2 chapter to it. It's only like 25 pages extra onto the page, and it's a fantastic overview of H2. There's an extension for Firefox and Chrome that essentially gives you a sign of what protocol you're speaking to the server. I am addicted to this thing. I can no longer not look at that little lightning thing, any website that I speak to. Chrome DevTools has some cool tools, including a protocol column, which is new. You got to add it. It's not on my default, so right-click on the columns and get it. There's a net internals panel that tells you what's happening with the individual connections that you have. Here you can actually see the frames go by, which is really interesting. And it's the output of this that is the input to the priority graph that I showed you. I can't have a talk without talking about Wireshark. It's the greatest tool in the world. Because everything is TLS, decrypting H2 is very difficult. But that link right there will tell you how to do it. And that's what it kind of looks like on the wire. Curl now has H2 support. I don't think it's the default curl that comes with the distributions. There's a new version of curl, but it has it. It's there. That's what it looks like. And there's another tool that looks like curl called ng-http. Actually operates a lot like curl, but gives you a lot more debug information about how you're communicating with the server. And actually, I think curl uses ng-http as its engine. Here's a bunch of others, a lot of tools. Actually, not enough, but they're coming. And there's actually, the working group keeps a list of them. Okay, let me finish up with this. My intent was not to bum you out at all. My intent was just to take a more practical look at the protocol and just not be so rah-rah about it. There's parts that are good, there's parts that are bad, it's complicated, but it's probably better for us going forward. We finally iterated on our protocol after 20 years, and I guarantee you H3 is not going to take 20 years. So we're in a good place right now. It's okay if H2 isn't perfect, but it's up to us to sort of learn lessons, give back to the community, and make H3 even better. The group, all the authors are hungry for data. So anything you can do on your own that feeds back into the system is going to inform H3. You got to do that. That's going to be a great service. We have a lot of learning to do, and it is time for us to think about how we architect our apps to best leverage the features of H2. One of the reasons that it's not performing as well is probably because we're not built for this protocol. Let's build things for this protocol. And I can't implore you enough to do these tests and publish your results so we can learn from it. What I did is just one thing in an isolated lab. What you have in real-world data is going to be a lot more powerful. Do I have time for questions? I have 5 minutes? Do I have 5 minutes? Somebody give me a thumbs up? No? Thumbs up. 5 minutes. Any questions? I gave you a lot of data. I really came at you hard, right? Sorry. There's so much. That was 200 slides, by the way. Yes?
Just kind of curious, how close are the implementations of HTTP 2? One of the big problems that I've had with HTTP 1 and 1.1 is various differences between clients and servers. When there's much differentiation.
Yeah, good question. The question is, how different are the implementations? So I've looked at H2O more than any other. The implementation is pretty solid, but it's still iterating. My guess is the place that they differ the most is the way they handle priorities. And that is an area that is utterly uncharted. We have no idea what the right thing to do there is, or we have no interface between the application and the protocol to dictate priorities, right? This is sort of up to the browsers right now. So I'm relatively certain that you're going to see lots of different implementations there. Core protocol with framing and things, I think they're going to be basically the same. The only difference you may see is push, the way they're handling push, and that would be in order of things. Does the push promise show up at the right time? Probably does. But does the push stream come when it's supposed to, or does it wait before the thing that references it, or things like this? So I think you'll see some differences there. Because we're so early in the life cycle of this protocol, I would expect more differences that you're probably comfortable with. But that's not necessarily a bad thing. I think that's a good learning place for us. Anything else? Yes? I don't know about HA. I think HA proxy, yes. I think ELB. Didn't ELB just announce H2? Amazon had an H2 announcement a couple of days ago. CloudFront had an announcement a couple of days ago, so not ELB. CloudFront has it. Most of the CDNs have it, not all. Not all the CDNs have it. The load balancers are going to have it if they don't already. And I'm pretty sure HA proxy has it. If not, it's going to be very soon. Oh, those guys have it. HA proxy has it. Nginx. I know Nginx has it, and I know Apache has the module now. Yeah. And the list is there, so check out the Wikipedia page. There's a big list of all of them. Anything else? Yes? Yeah.
So you had kind of alluded to it, but can you expand on, is this something that we're going to see inside the data center? Is H2 have any, are there applications for H2 outside of that?
So is H2 useful inside the data center? Is that your question? So that's a good question. And I think the answer has to do with, were you surprised that it was a good question? It was a good question. I think the answer has to do, so I think I think of H2 as a browser protocol. Like that's the point at which I sort of came to terms with how weird it was. I was like, okay, it's a browser protocol, things need to happen at the same time. But then I'm often wrong. And somebody told me that somebody moved to H2 for their API calls because it reduced the connection load on their API endpoints. And that sort of makes sense to me. Now, for a single API call, it makes no sense to use H2. But if there's a keep alive API client that's constantly making requests and the connection load is high on an API endpoint, sure, you probably cut it down by 6, 8-fold, and you have less connection load on that server. So that kind of makes sense. Binary protocols are easier to process. Maybe this will be a lower overhead for your servers. So I think the possibility is there. I still think of it as a browser protocol, but I don't think it's outside the realm of possibility that you're going to find uses for it inside the data center. I'm going to be around for a while. If you have any more questions, come find me. Thank you for your time.